Okay, this is lesson 6.7, Applications of Sinusoidal Functions, part 1. So in part 1, we have 3 word problems we're going to look at today. I'm going to do 2 in this video, save 1 for you to try, and then tomorrow we will have more word problems in part 2. Let's start with my paper T-Rex. Mr. Riseborough's paper T-Rex goes nom nom when you turn the handle. The height h of the end of a handle relative to the horizontal as it is rotated at a time t is given by the function h of t equals 6 cos 180t, where t is in seconds and h is in centimeters. Where is the handle positioned at 16 seconds? So for the first question, we're just going to take the function and we're going to find the height at 16, so h of 16. So h of 16 would just be plugging 16 into our function. We get 6 cos 120 times 16. And we can just do direct calculation here. Make sure your calculator is in degree mode. Mine is in the wrong mode. So let's get a degree mode. 6 cos 180 times 16. And we get 6. What does 6 represent? Well, 6 represents in h in centimeters, 6 centimeters. So the height after 16 seconds is 6 centimeters above the horizontal, so it's relative to the horizontal. So if you think about, well, we're going to draw it here and see, but if you think about a handle, it can go around, right? So the horizontal will be right through the middle. So at its horizontal, it would be 0, and then you can go up or below, I guess above or below the horizontal. So in this case, after 16 seconds, we're 6 centimeters above the horizontal. B says, how long does it take for the handle to make one full turn? Well, one full turn, it's asking for 1 cycle. And we know that a cycle is called the period. The relationship we have between an equation and the period is in terms of k. We know that k equals 360 divided by the period. So we can rearrange that equation and use that the period is just 360 divided by k. And the k value we have is 180. So if we want to know the period, we would do 360 divided by k. If k is negative, it would be the absolute value of k, so you would divide by positive. But 360 divided by 180 is 2, and we're working in time measurement in seconds, so we've got 2 seconds. At what time will the end of the handle be 1.4 centimeters above the horizontal for the 6th time? Interesting. Okay, so we need to think about what this function looks like. So what does this function look like? Well, it would be helpful if we knew a few more times, because right now all we know is times 16 is 6 centimeters. We can discern a few times just by looking at the equation. Our equation is structured as a cos equation with no shift. Positive cos with no shift. Cos function with no shift starts at a max. This is what our cos x parent function looks like, and that's what we have. And we've only done a couple things to the original cos function, is we've stretched it vertically, so our times are stretched. So instead of 0 to 1, we're stretched by 6, so we're 0 to 6. And that would make our bottom negative 6. So our amplitude 6. We have no c value. C value is 0, so that means our axis is around 0. So we've got a good sketch here. And if k is 180, that means one whole period would be 2 seconds. That means one cycle is completed in 2 seconds. Now we have kind of a picture of what our graph looks like. Now 1.4 centimeters above the horizontal for the 6th time. 1.4 would be, well, if 3 is here, 1.4 would be like right here and right here. In the first cycle, we're going to hit it twice. So that means if we want to find where it's the 6th time, we got to repeat this cycle a couple times. So I'm going to draw that down here. Now we got an opportunity to draw a little bit more detailed graph. Nice sketch here. So we got 0, we know our max is 6, we know our min is -6. So we got 3, -3, 1.5, 4.5. A little bit better of a scale here. We know 1 cycle's every 2 seconds, and if we want to get to the 6th time, we're going to have to do a couple cycles. 2 cycles would give us 4 times that it hits 1.5 or 1.4. 3 cycles would give it 6 times, so we got to draw at least 3 cycles. Each cycle is 2 seconds, so we got to make a scale go to at least 6. So let's say 2, 4, 6. That'd be 1, 3, 5, 2, 4, 6. All right, so we've got to get a cycle in there. Let's give it a shot. So we start at the max. There's our first cycle. There's our second cycle. There's our last cycle. So there's a nice sketch of what we're working with. And we want to see where it's 1.4. So I'll label 1.4 on there. First time's here, second time's here, third time, fourth time, fifth time, sixth time. So we got to figure out what time that is. Well, we can see it's after 5, before 6, probably after 5.5. We can approximate what it is. But to calculate it, we've got to do a little bit of math. So using the equation, you can figure out the first time that it'll hit. So we'll do that, and then we'll use the Cartesian plane to solve for the 6th time. So let's do a little bit of math. We know we want a height of 1.4. We want to know the time. So we have an equation. H of t equals 6 cos 120t. The time we're given is 1.4, or the height we're given is 1.4. We want to solve for t. If we do this, we can find information about the time that we're hitting the height of 1.4. So let's solve. We'll divide both sides by 6. And we get 1.4 over 6 cos 180t. If we do cos inverse, we can find the angle of the handle relative to the horizontal, but we want the time. So cos inverse will give us the related acute angle, but we want the related acute time because we're working in time. So we can do cos inverse of 1.4 over 6, but that's only going to get rid of the cos, and we still have this 180t. So if we want to find the time, we've got to divide by 180. And this is going to give us a related acute time in the sense that 1 full rotation would take place between 0 and 2. So we're going to get some time between 0 and 2, and it will be our related acute time. So it would be a time in the first quadrant, and we'll graph and see how that relates to our sketch over there. But let's figure out this time first. So we've got cos inverse of 1.4 divided by 6 divided by 180. We get, 0.43. And this is not our time answer. This is our related acute time. So we can use this on the Cartesian plane. On the Cartesian plane, since we are doing cos inverse of a positive ratio, we ask ourselves, according to Castro, where would cos be positive? Well, cos would be positive in quadrant 1 and quadrant 4. That's why we have 2 answers for each rotation, because we hit the terminal arm twice. once in quadrant 1 and once in quadrant 4. We're not dealing with angles this time. We divided away 180. We divided an angle away. We were left with a time. Because one rotation is not 360 on this example, one rotation is in terms of time from 0 to 2. So that means our Cartesian plane starts at 0 and goes to 2, which would make a half rotation 1, quarter rotation would be 0.5, and a full three-quarter rotation would be 1.5. And if we look at our scale, that kind of makes sense. Half a rotation would be from max to min, that's 1 second. That's why we have 1 second. A full rotation takes place over 2 seconds, that's why we're back to the max again. How do we use this 0.43? 0.43 is the time it takes to go to the first terminal arm, and it's mirrored in the time that it takes, or the time you're short of finishing the rotation. It's like your related acute angle, but since we're working in time, it's like a related acute time. How do we use that to figure out our times? Well, we can use this picture to figure out the first and second time, because this is the first rotation. Time 1 would just be 0.43. That's how long it takes to get to the first terminal arm. Time 2 would be from here all the way to here. And time 2 would be not all the way to 2 seconds. You're short 0.43. So that'd be 2 minus 0.43, which is 1.57. Now, 1.57 is not our answer because we want the 6th time. But if I put these on the graph, you can see what these are. Time 1 is right here. Time 2 is right here. We want time 6. So the way we find time 6 is we just start adding the period to our first 2 answers until we get to the 6th time. So if we want the 3rd time, it occurs early in the second rotation. We would take our first time and add a period, 2 seconds. So this would be 2.43. If we add 2 seconds to our second answer, we get 3.57. That's the 4th time. If we add 2 seconds again, we get the 6th time. So to show the math, if we want time 6, we take our answer for time 2, and we add the period to get to 4, and we add the period again to get to 6, which would make our time 6 answer, I am out of room here, but 1.57 plus period twice is 4, time would be 5.57 seconds. That would be time 6. So after you find your first 2 times, if you want an even number time, you add the period to the first even number time. So time 2, if we add it once, we get time 4. If we add it again, we get time 6. If you want 3, 5, if you want time 11, you would add 2 enough times to get to 11. Every time you add the period, you're adding, or you're going to the next odd time. So if we want time 11, we would add the period to get time 3. We'd add it again to get time 5. We'd add it again to get 7. Add it again to get 9. Add it again to get 11. So for any of these questions where you're asked to find a time that's not the first or second time, you find the first and second time, and then you just add the period over and over again until you get to the time you want. So we'll do another example of that here in question 2. Question 2 is a Ferris wheel question. A Ferris wheel has a radius of 25 meters, its center is 26 above the ground, and it rotates once every 50 seconds. Suppose a rider gets on at the bottom at time 0, sketch a graph to show the rider's height, and find an equation. So I'm going to use this picture of the Ferris wheel here to demonstrate some key numbers. It says the radius is 25. The radius would be from the middle to the top and from the middle to the bottom. This would be your radius, which if we think about this in terms of sine function, from the middle to the top or the middle to the bottom is also the amplitude. So if you're ever given the radius, radius is the amplitude. So if we put this on our diagram, we get 25 and 25. Its center is 26 meters above the ground. So I'm going to put this on over here. This will be our vertical scale. The center is 26 meters. So if we go up 25, we get 51 meters. If we go down 25, if we go down 25, we don't get 25, we get 1 meter. Which kind of makes sense because it means there's a little platform here. And that would be 0. So here's our vertical scale. And how does this help us? Well, it helps us because this is a lot of key information. Here's the radius, which is also the amplitude, so I'll label it with different letters. Here's our vertical scale of our graph. 51 is the top, 26 is the middle, 1 is the bottom of a cycle. So if we want to draw our sketch here, .26 is the middle, that's our axis. 1's the bottom, 51's the top. These are our heights, and they're in meters. And these are our times. We have information about time. Every 50 seconds, and the rider gets on the bottom at time 0. Well, the bottom would be here. That'd be time 0. And we'd rotate once every 50 seconds. Let's show 2 rotations. So that means we got 50. Well, let's show 3. 50, 100, 150. 3 rotations. So we start at the 0, that means we'll get back to the bottom at 50, which means at 25 would be at the max, which if we keep splitting, 12.5 would be in the middle, and 37.5 would be in the middle. We can connect and get our first rotation. We're back at the bottom at 100. We're at the top at 75. And we're in the middle, So continue. Back at the bottom at 150. Top would be 125. There's our last cycle. There we go. A nice sketch. Let's find the equation of this function. Well, some important information was given. We were given the amplitude, or the radius, of 25. The axis we can see right on the graph is 26, where it's at the center. K we can calculate. It's 360 divided by the period. Period's 50. Which means we have 7.2. And now we just need to pick a model. Since we're starting at the bottom, we can use negative cos. And since we aren't shifted, it's the minimum at the bottom, we can use a d of 0. So now we can write our function. Let's define h as our height and t as our time. So let's call this h of t. Negative cos, so we got amplitude 25, we got negative 25 cos. K is 7.2. No d value, so we put t. And our c value is 26. And there we have our function. So what can we do with that function now? Well, basically now we can do the same questions we just did in 1. We can answer some questions about position after a certain time. We can solve for some different heights at different times. Let's give it a shot. What's the height of the rider after 430 seconds? Well, let's remember our function. We just wrote it, h of t, negative 25 cos 7.2 t plus 26. So after 430 seconds, well, we just plug 430 in. So we get h of 430, negative 25, cos 7.2 times 430, plus 26. All right, let's do some math. Making sure we're in degree mode, we get negative 25 cos 7.2 times 430 plus 26. We get 46.225, we'll go 46.2 meters. Now if we go back and look at our sketch, we could continue the graph and come up with the same estimate. If we're 46.2, getting pretty close to the peak. So we're either on our way up or on our way down. But if we continue the graph, we can figure it out. So we're somewhere around here, either on our way up or on our way down. D, when does the rider reach 40 meters for the second time and the 9th time? That's poor formatting. Which question was I trying to do? Which the formatting got taken from over here on the side. I think this is meters for the 9th time. Sorry about that. Yeah. When does the rider reach 40 meters for the second time? So we're going to do one that's just on the Cartesian plane, and then we'll do a secondary example where we have to do what we did in the first question. Okay, so 40 meters, we can solve for it and find a related acute time, and then we can use the graph of the Cartesian plane to figure it out. Now, what do we know about the Cartesian plane? Well, I'll draw it over here. We know we're not talking about angles anymore, we're talking about times, and it takes 50 seconds to do a full rotation, which means 25 seconds is a half rotation, 12 and a half would be a quarter, and 37 and a half would be 3/4. So we got some time scale now. 40 meters would be near the peaks, but let's solve for it. So we got 40 meters, that's what's given, we want to find the time, so we got negative 25 cos 7.2 t plus 26. So we can start by subtracting 26 from both sides. We get 14 equals negative 25 cos 7.2 t. Divide both sides by negative 25. We get 14 over 25, but negative is cos 7.2 t. So at this point, if we want to find a related acute angle, or a related acute time in this case, when we do cos inverse, we're ignoring the negative sign, and then we're using the negative sign to decide which quadrants our solution is going to be in. So according to cast rule, cosine should give us a negative answer in quadrant 2 and quadrant 3. So that takes care of the negative sign. And now when we do cos inverse, we'll get a answer for 7.2 t, but we ignore the negative sign. The negative sign tells us our quadrants. Cos inverse tells us our related acute angle. 55.94. But since we're not working in degrees, we're working in time, we need to divide away k to get this in terms of time. So if we divide, I'll show the work here, divide by 7.2, we'll end up with a related acute time, which time, not time 1, be our related acute time. So back to my calculator, divide by 7.2, we get 7.7 seconds. I'll call it 7.8. And this time goes on our diagram as the related acute angle, in this case the related acute time. So it would go here and here. So if we want the first and second time, we're looking at times relative to 25. 7.8 before 25 would be time 1, but if we want time 2. Time 2 would just be 7.8 seconds after 25. So we go 25 plus 7.8, and we'll get our answer, which is 32.8 seconds. Let's try a very similar question, but this time, you know what, let's save ourselves a little bit of work. Let's just turn this into 40 for the ninth time. I've really modified this question. But the work would be the exact same. We do all the same work, we get the same time, but now that we want the ninth time, we use our diagram a little bit differently. So same diagram. Just going to redrive here. Our answers are in the same quadrants. We get the same time, 7.8, 7.8. We already know time 2. It's 25 plus 7.8, which gave us 32.8. But since we're looking for the ninth time, we're looking for an odd time, we also need to find the first time, time 1. Well, time 1 would be, since we're relative to 25, 7.8 short of 25, because this is time 1. Time 1 would be 25 minus 7.8, which is 25 minus 7.8, 17.2. That's time 1. So now if we want time 9, well, time 9, we would take 17.2, our answer for time 1, that's time 1, and we would add the period. Our period's 50. If we add the period once, it would take us around one full rotation and then back to our first terminal arm, which would be time 3. So if we add 50, this gives us time 3. If we add 50 again, this gives us time 5. If we add 50 again, this gives us time 7. And if we add 50 again, this gives us time 9. So 50 and 50 is 100. That means 200, which means our time 9 answer is 200, 17.2 seconds. Okay, so I'm going to save 3 for you. 3 is very similar to the question we just did. Give it a shot, see if you can come up with some answers. Check your answers as the solutions are posted, and if you have questions, feel free to ask tomorrow.